Our next speaker is Lonnie Thompson, who is a distinguished university professor at the School of Earth Sciences and a research scientist in the Bird Polar Research Center at Ohio State. He has been a key person in the field of ice core paleoclimatology, and he's looked at the changes of the ice cores in the highest tropical and subtropical ice fields. You might note that his wife, Lonnie, Ellen Thompson, was sworn in this morning, if you want to call it that, as a member, and they essentially constitute a very strong team of scientists who've looked at ice cores and have given us very valuable information about how things are changing and the past climate. Lonnie has worked primarily in the American Andes, the Himalayas, and Kilimanjaro ice fields, and has made some very valuable discoveries in the effects of the changing global scale phenomena such as the El Nino and the monsoon systems. He's won the National Medal of Science on the Tyler Prize, which is a prize, it's a world prize for environmental achievement, and other awards. He's a member of the National Academy of Sciences, and he became a member of the American Philosophical Society in 2006. He actually has another unusual award, and that is that he has a heart transplant, and he holds the record for going up to high altitudes to take these measurements. And after he was taking on these measurements for a long time over some of these mountain areas, and now after having his transplant, he is able to get back to the same area and work with his students and colleagues in taking more ice cores. So I'd like to introduce Lonnie, and he can get started.
Thank you very much. It's a pleasure to be here in many ways. And I want to talk about what our team does. We have drilled ice cores around the world in my life, and I must say it could not have been done without team effort. That team effort are people that make up our group that have changed over the years. Ellen is a constant in that team, but we work internationally, and we could not do what we do without full collaboration with countries and people around the world. And I think this is the future. If human beings have a future, it's in working together. And so I want to cover a number of things today. I want to talk a little bit about the history. I'm going to talk about how we do this. But we have to have lightweight equipment. And if you think about bringing a frozen ice core out of the tropics, this can be a challenge. Glaciers serve as recorders in that they record annual snowfall and everything that's in the atmosphere when that snow falls. But they also work as indicators, because if it gets warmer, they retreat. If it gets colder, they advance. So they are also an indicator of that change. I'm going to talk about briefly about the quest for the oldest ice outside of the polar regions, and a large-scale isotopic climate linkages that are driven largely by equatorial Pacific SSTs. And then I'll wrap up with evidence for amplification of the recent warming at high elevation where these glaciers are located. So first of all, we forget that we live on a sphere, but because we do live on a sphere, 50% of the surface area of the planet is in the tropics, between 30 north and 30 south. We have about 70% of our 7.3 billion people living in this zone, so it's important to understand natural variability as well as human-driven changes. As Claire mentioned in her excellent talk this morning, in the tropics is where we get the water vapor that goes into the atmosphere, and this is our most important greenhouse gas on this planet. And so to get to the polar regions in the tropics, you have to go to very, very high elevations. So these are the places that our team has drilled over the last 40 years. And it's really a global initiative, but it's been carried out with one project at a time through those 40 years. In order to do the analysis, you have to have laboratories, class 100 clean rooms where chemistry and dust and black carbon's measured. We have isotope labs for measuring isotopes of hydrogen and oxygen. You have to have a storage facility. We have over 7,000 meters of core stored at minus 30 degrees C. It's the only tropical collection of ice on Earth. And we have to design and build the drills that we use because they have to be lightweight. You got to be able to get them up to 20,000, 22,000 feet. So it really takes a team in order to do this. This is what a lightweight drilling system looks like, drilling at the top of the Calcaya ice cap in the Andes in Peru. Power sources, our team built the first solar power drill in 1983. It's a wonderful energy source and it doesn't contaminate the environment. But we've also modified diesel generators to run at high elevation and cold, low oxygen environments for running these drills. Logistics, if you're in Tibet, there are no roads and you have to make your way across. And again, these are challenges for getting the ice cores back out of these regions. But just to give you an idea of how this is done, if you're in the Himalayas, we use Sherpas and porters above 20,000 feet. But when you get down to the edge of the glacier, you're still 4,000 feet from where the trucks can come out on the plateau. So then what do? Well, you have to use the local logistics. That turns out to be yaks. These are insulated boxes. We have 6 meters of core in each of those boxes, 12 meters to a yak. We drill 500 to 600 meters of core, and therefore you have to have a whole herd of yaks to get those down to the trucks. Then there's a dash to Lhasa where there's a freezer. They're air cargo to Beijing. They go through Chinese customs. Air cargo to Chicago. They go through U.S. customs, and then they're trucked to the university. So it's a major effort, and it's a team effort. The largest ice cap on Earth is the Calcaya tropical ice cap. It's in the Calcaya ice cap in the Andes of Peru, and you can see it here. This is a place where our career in the tropics started. And you can see on the margin of this ice cap these very distinct annual layers. They're 2 to 3 meters thick, and it's easy to see how you could take a drill and recover a history of that record. And that's what we have been doing. This is what an ice core looks like when it comes up. And they are truly amazing records. This is the last 1,000 years on Calcaya. This is decadal averages of isotopes. This first core was drilled in 1983 and was analyzed in Woody Dansgaard's lab in Denmark. And 20 years later, these were based on 6,000 bottled water samples because at the time we didn't have the technology to keep the ice frozen. And this is 20 years later on a frozen ice core from the same area. And you can see it's warm from 1,000 to 1,500, the little ice age in here, then the warming in the 20th century. And because you have those annual layers, you can also reconstruct how did precipitation change. And so over that same period of time, you can see it was dry up to about 1,500, initial part of the little ice age wet, then dry, and then wetter in the 20th century. So they give us a wonderful history of the past. Well, in order to look at high-resolution variations in our climate, we need to have these annual histories. And the longest annual history in the tropics comes from Calcaya. It goes back 1,500 years. We have another one from Corapuna that goes back 300 years, and these are in the southern Andes of Peru. And this is over on the top of the Himalayas. And when you have these annual records, you can start looking at large-scale phenomena. And one of the things we're interested in is how El Nino Southern Oscillation has varied through time. Are there other modes of variability that we do not see in the last 100 years? So this is one of the phenomena that will connect these sites that are 22,000 kilometers apart. If you look at the isotopes, and you look at sea surface temperatures, and you look at the correlations from 1870 to 2002, they're very much correlated with sea surface temperatures in the eastern tropical Pacific. And if you look at on land, if you look in Peru, these are weather gauge measurements of what happens during an El Nino in Peru. Southern Peru is always in a drought. These are the last three major events, 82, 83, 97, 98, and 2015, 2016. 2015, 2016 was different in that there was drought throughout the Andes during that event. If you look at these sites, and you look at sources of dust, the Ganges Plain over in India, here's where Dasupu is located. The monsoons carry the winds across these. If you're in South America, there's Libyan High. It circulates the air around here across the Salar de Uyuni, the largest salt flat on Earth. And these become source areas for dust that can be recorded in the ice cores. If you're in Bolivia on the Salar de Uyuni during a La Nina, the opposite phase, sometimes it will rain and there's a film of water on that salar. But this is what it usually looks like. And when the wind blows, this material is picked up and carried and it gets deposited. And what is amazing, when you look at this one period, I'll just look at one, drought in the 1790s, and we have good evidence that this was caused by several El Ninos back at that time. And we have it recorded in things like chloride, which is picked up by the wind. So here are 250 years of record. And you can see the magnitude of this event in the Andes of South America and also over in the Himalayas. Then you can look and say, this is a period where we do have documented records. And if you look in India in the late 18th century, this was the East India drought with 1791 El Nino was at its core. 11 million deaths in India during this period of time, and 600,000 in 1792 alone. And you think about this, this is before India had 1.3 billion people, and China has 1.4 billion people. So these impacts would be tremendous in today's world. And you can look around the world at that time, and there were severe droughts. These are very similar to what we've had during the smaller El Ninos in today's time. And there was great social upheaval around the world. There were 4 revolutions at this time. So this connection between climate and people is extremely important. If you look at loss of ice on Earth, all these red areas show where we're losing ice. We saw Antarctica and Greenland this morning. There is another pole that we're very interested in. It's the third pole. It's the Himalayas and the Tibetan Plateau region. And in fact, with our Chinese colleagues and German colleagues, we launched a program called the Third Pole Environment Program to try and understand what I believe is the least known region of the world. And it's very important because it covers 5 million square kilometers. It has one of the largest glacier stores of fresh water, over 46,000 glaciers in that region, sometimes referred to as Asia's water tower. The glaciers feed Asia's largest rivers, and they help sustain about 1.5 billion people. So what happens to those glaciers going forward becomes very important for water resources. Now, with our Chinese colleagues, we've been able to drill cores across Tibet, and if you look at these records, the deepest core comes from Glacier in the far northwestern part. All the other records are mainly Holocene. You can see the enrichment taking place coming up to the present in all of these cores, but only this one contains the last glacial cycle outside of the polar regions. So as part of this TPE program in 2015, we had a party of 60 people from 5 countries to go into this site and our objective here was to acquire the oldest ice core paleoclimate history outside of the polar regions. And this is an amazing place. We have the highest equilibrium line altitudes on the plateau here, the coldest temperatures, the driest conditions. This is where you're going to have very old ice preserved if it's in that part of the world. The ice cap is very large. It's 35 degrees north, and what makes it unusual, it's the same latitude as Durham, North Carolina, or Memphis, Tennessee. And so here's an ability to connect with the Antarctic and the Arctic with something in between. And we already know that we have the full glacial cycle here on Glacier at 35 degrees north. We know that the differences between the glacial max and the interstadials during that last cycle are much larger than what we find in the polar regions, in the isotopes in the polar regions. But you can also see the methane measurements that are made in the bubbles in the ice in Antarctica, and you can see how these line up very nicely with the warm periods that we see, these 22,000-year cycle recorded in this core. We didn't publish the lower 43 meters of this core because we didn't have the dating tools to date this in 1992. We do have that now, and the core is currently being dated. We believe it'll be well over 500,000 years, but that record is being developed. If we look at the more recent past, in the tropics, these are our instrumental records of temperatures. You can see how they have increased. These are 5-year averages of a composite of our isotopes from these cores, and they all show this enrichment taking place in the isotopes as the temperatures warm in that part of the world. And the beauty of ice is it gives you a perspective. We can take these cores and in the tropics, in the low latitudes, create a composite. These are decadal averages for 2,000 years. This is the medieval climate anomaly. Here is the Little Ice Age, warming in the 20th century. We can compare that with other reconstructions, and it is always the balance of evidence. These are based on tree rings and the historical records in the Northern Hemisphere and the instrumental record. And what really stands out is what's happened in the last 50 years. Now, the thing is that people have a difficulty with isotopes. If you do this at the U.S. Senate, this is a problem. But this is my favorite quote. This comes from a book called A World Without Ice by Henry Polly. And it says, ice asks no questions, presents no arguments, reads no newspapers, listens to no debates. It's not burdened by ideology, and it carries no political baggage. As it changes from a solid to a liquid, it just melts. And I'm going to show you what's happening to the ice. I took this when I was a graduate student, 1977. I showed you this early on. Same place in 2002. We are losing the history that are in those cores, but we're also losing a very valuable water resource for the people who live here. This is the largest outlet glaciers that comes from that large Quelccaya ice cap. This is what it looked like in 1978 when we first started mapping it. It's going to morph into 2011. So this is what it looks like today. This lake started forming in 1991. It's 60 meters deep, covers 84 acres. And it's happening throughout the Andes and throughout the Himalayas. As this glacier retreats, there are things coming out from underneath. These are plants, wetland plants that are in growth position, perfectly preserved. These plants can be collected, and they can be carbon-14 dated. They tell us this ice cap hasn't been smaller in 5,200 years. Otherwise, these plants would have decayed. But what's amazing is how fast this glacier is retreating. Here's the ice, 2002. 3 years later, here's the plant. There's the ice. And as the ice has retreated, more plants have come out. And those plants can be dated. And here is an example. This lake didn't exist in 1984. This is all ice. All the plants collected over here were 4,700 years. This island was emerged from underneath the ice in 2011. Those plants are all 6,300 years in age. And we just collected plants there in 2016. They're 6,600 years in age. So they give us a perspective on the change in that part of the world. This is happening around the world. Here's in the Himalayas. Here's an old photo from 1921, same place in 2009. We've worked with our Chinese colleagues to look at the area reduction of 7,090 glaciers in this region. And this shows how they are retreating since 1970. Main retreats are in the Himalayas, lesser amounts as you go in the interior and up to the northwest. But mapping out how that ice is changing becomes extremely important. Kilimanjaro in Africa. Oldest photo we could find, 1912. Here's what it looked like in 26. The first map was made in 1912, and from 1912 to 2013, we had lost over 88% of the ice that had been there. And we drilled in 2000, and since 2000 up to 2013, we had lost 40% of the ice that had been there in 2000. And we put a stake through this small glacier, the Furtwanger, in the center. And that stake has been measured ever since we left it in 2000 by Doug Hardy at University of Massachusetts. And you can see how the ice was thinning all during that period, and this site disappeared in 2013. You can't go and get these records now. And this is happening to these glaciers around the world. This is the photo of Furtwanger in 1999. You see the ice goes right out to the crater rim. Here is 2015. The crater rim is over here, and you can see how the ice is disappearing. That ice will disappear. Now, I'm going to take you to a really remote glacier that's in Papua, Indonesia, or what we used to call New Guinea. Most people don't know there's a glacier there, but it's the only glacier between the Himalayas and the Andes. And we found some old photos here. This is what it looked like in 1936, 1991, coming up to 2001. We drilled there in 2010. This was really a salvage mission to get ice out of this before these glaciers disappeared. So we drilled here and up here. The amazing thing is how it's changed since 2010. So here we are, this is 2010. Now you're going to watch this, it's going to go to 2012, 2014, 2016. Watch what happens to this glacier. Notice these holes developing here and how this is thinning in this area as we come forward in time. And then by the time we get to September 2016, it's separated into two glaciers. And our latest photo was taken on November 23rd, 2016. This is what it looked like. This is what it looked like 6 years earlier. This glacier will disappear. One of the questions we get when we work in these areas is, when is this ice going to disappear? Very hard to answer that question. But one way you can do it is you can look at all the maps that have been made. In New Guinea, the first map was made in 1936. And here are all the maps coming up, and you can project these out, and you can see in the next couple of years this glacier will be gone if we continue on this same line. You can look at Kilimanjaro in Africa, and you can do the first map in 1912, and you can come forward. It'll last a little longer. It's a little bigger, a little thicker. Kelkaya, the largest tropical ice cap on Earth, you can put a second-order regression curve through these area changes over our measured period and project that out. It will be gone by around 2060 AD. So this ice will disappear. And the question is, why are they retreating so rapidly? And and you can see this actually in the isotopes. If you look at the glaciers that have been drilled across the Tibetan Plateau, going from the lowest elevation to the highest, and you look at the slope of this isotope line from 1990 to 1939, you see it's here. And all sites in the last 50 years have been the most enriched in the last 1,000 years. And if you look at these, you can see the higher you go, the greater that change has been. The Intergovernmental Panel on Climate Change models that predict future temperature change, this is a transect from 60 north to about 50 south, project this 3-degree warming to occur at the surface. But up where these glaciers are located, that is projected to be twice as high. And this becomes extremely important for water resources for people who live downstream from these sites. So let me conclude by saying that the Tibetan Plateau in South American Altiplano is separated by 22,000 square kilometers. document large-scale teleconnections on both sides of the Pacific basins. The large climate linkages are driven in part by SSTs and INSOs. An extreme climate event recorded in these high-resolution cores from 1789 to 1800. This event has had large-scale impacts as recorded in human history and was connected but not synonymous with INSO. New ice cores from the Glacier ice cap in northwestern third pole region offer potential for reconstruction, very long series over 500,000 years that can provide context for understanding climate, atmospheric, and environmental variability in one of the least studied parts of our planet. The most recent 50-year period that all third pole ice cores have in common, 1940 to 1989, is the most isotopically enriched. The largest modern isotopic enrichment in the third pole ice cores occurs at the highest elevations. This is consistent with our meteorological observations, supports modeling results of elevation-dependent warming, and particularly in the low latitudes. And finally, glaciers are retreating around on the world's highest mountains, thereby threatening a valuable water resource for the people living downstream and resulting in the loss of a very valuable archive of our past. So thank you very much.
Questions?
Hi, Howard Gardner from Cambridge. Thanks for a very stimulating presentation. I have a political rather than a scientific question, but I imagine it's one on many people's minds. You're working in all parts of the world, which appear in the newspaper with various kinds of political regimes, and you're also moving material and personnel all around the world. Is this occurring enough below the political terrain that it can continue indefinitely, or is what's happening, whether it's in Peru or New Guinea or in the Poles or in the United States, likely to impact the cooperative studies that you're doing?
This is a question that keeps us up at night. Not so much for me. I've been at Ohio State 40 years, but I'm really worried about the young people and their careers and even their decision-making process of whether there's a future in this type of research. And to me, this is our greatest loss, because our greatest hope is in our young people. And I would say that the thing I found in working in now 16 countries outside of the polar regions, that once you get by the government, by the people are very good, and I'm totally convinced there's far more good in this world than bad. And that is what I'm counting on. And when, like we just drilled over in the Western Kunlun, that in that party, we had Russians, we had Chinese, we had South Americans, we had Americans, and we're working in an extreme environment. I mean, there's not much oxygen up there. You're at the end of the food chain. The winds are howling. It's minus 35 degrees, and yet we can work together to accomplish a mission. And to me, one of our big goals with that third pole program is bringing 14 countries in that region that don't talk to each other. Get the scientists talking to each other and getting communication and understanding that, yes, we're just people. And I think if there's a future for us, we are going to have to work together to solve these problems that is so evident in all of our observations. And so it's a very good question, and I think I've been at this for 40 years, but I do tell my graduate students that when I started on Kelkaya, and I went to NSF and asked for funding to polar programs, because they were the only people that funded polar research, the program manager listened. We wanted to connect Antarctica with Greenland. And he looked at me, he said, Lon, I can't fund that. Sounds interesting, but I can't fund it because it's not north of the Arctic Circle, we're south of the Antarctic Circle, and that's our mandate. And I was in Antarctica in 1974, and I got back then they had telexes, from the program manager that stated, I have funded all of my real science projects and I have $7,000 left. What could you do on that Quelccaya ice cap for $7,000? And I telex back and I said, I think we could get there. And that's where it started. So I think people, all of us can change the world. And it's a very important message for young people. They can change the world. And hopefully they can do a better job than we have been able to do.
Have you also studied the highest glacier in the Arctic, or is it a stable situation?
In the Arctic?
In the Antarctic, sorry. Antarctic.
Ellen does the drilling in Antarctica. We've drilled at the South Pole and the Pole Remote in far eastern Antarctica. These are very high elevation ice fields in themselves. But I haven't. I drilled on the Antarctic Peninsula. Those are, it's a higher part of the Antarctic ice sheet. But Ellen, that's her forte.
Philip Gingrich, Ann Arbor. You were going to tell us what's the oldest ice on Earth.
Yeah. Okay. The oldest. Let me show you the oldest ice on Earth as it exists today. This is from East Antarctica. This is the Epica core. It goes back 800,000 years. There's a major effort right now to find the oldest ice on Earth. Most people believe it will be found in Antarctica. However, because this ice sheet is over 200 meters deep, there's a geothermal heat flux coming from the bottom. There are 435 lakes underneath. There is a stream system underneath. And the only way we know from the physics of ice that you can remove time is to melt it. And so the question becomes, where will you find the oldest ice on Earth? But certainly there are major efforts underway right now by many nations to find it in Antarctica. But why I have this up, and it relates to the subject of this conference, is that the beauty of the ice is it preserves everything. And in these bubbles is the atmosphere of the past, capsules. And we can measure all those greenhouse gases that we're concerned about today. And here's the CO2 record going back 800,000 years. And here is the temperature record from Antarctica, from the isotopes going back over that same period. And you can see the correlation. When CO2 is high, the Earth is warm. And when it's low, 180, 200 parts per million, we have the big ice advances. And what Warren Washington was showing at the beginning, here's where we are today. And so there is no analog to where we are today with CO2 in the atmosphere based on this 800,000 year history from the ice. And what we're really concerned is this trajectory that we're on. And what is that going to do with the climate on the Earth? To me, this is probably one of the icon records that have come out of the ice. And the reason they want to go back further is that we know that if you get back a million years, there was a major transition in the climate. How did these greenhouse gases vary over that transition? It's a perspective that we're looking for in the ice.
Yeah, actually, if I could just add an additional thing onto that.
Yes.
If you actually extrapolate that curve at the way that we're using fossil fuels, by the end of this century, we'll be up to 1,300 parts per million. Right now, it's at 400 parts per million. So if we don't start cutting back on fossil fuels, we're going to have a tremendous increase in the global warming.
I would also point out that there have been studies, geological studies, to look at when was the last time we were at 400 parts per million. And you have to go back about 3 million years to the Pliocene. And if you look at what the temperatures were at that time, they were about 2 to 2.5 degrees C warmer, and sea level was 72 feet higher than today. So you have to remember that there's a lag in this system. It takes a long time to warm up these ice sheets, these big ice sheets. These little ones respond fast. But the bigger ones takes time, and it takes a long time to warm the world's oceans. And most of the heat going into the atmosphere right now is actually going into the world's oceans.
Dr. Ostrager, and then a question in the balcony as well.
Yeah.
Go with Dr. Ostrager here.
I think the best records for the past temperature changes on the planet are your ice core measurements, if I understand things correctly. And then we're now doing climate modeling for the future based on what we're putting into the atmosphere. Here's my question. Does the climate modeling for the past agree with your observations for the temperature changes in the past? In other words, do we understand the climate well enough to predict what we're seeing there?
It's an excellent question, difficult to answer. But I would say that, first of all, when you look at a curve like this does not, our evidence for that greenhouse gases like CO2 causes temperature to rise came from physicists who studied these gases back, people like John Tyndall back in 1869, looking at how these gases absorb infrared radiation. And they were able to document how that would work. But I think what this shows us is that how when the climate of the Earth changes, CO2 has changed. And about a third of the warming when we come out of these ice ages is driven by increasing CO2 in the atmosphere, which is due to outgassing from the world's oceans, because warm ocean water can absorb less CO2 than cold ocean water. And this gives me concern when we think about the future, because the oceans are warming. Right now, they're our friend. They're absorbing a lot of this that we're putting in the atmosphere, but there's no guarantee that that will continue going forward. So your question is well taken, but science is something that progresses, and we learn, and it's, to me, we always have to go back to the balance of evidence that we have, and it comes from so many different disciplines, and all of them are extremely important for understanding climate.
Martin Kern from Princeton. You hinted a little bit at political consequences of climate change. You pointed to the 1790s, and then you showed us this slide of Tibet, the water tower of Asia, and you said there's 1.5 billion people who will be affected by what happens there. When you look at the funding of this kind of research, one would expect that the Chinese or the government of India pours in enormous resources to do more of what you're doing. Is that correct?
That's absolutely correct. I have been amazed. I first went to China in 1984, and there was hardly any money for research. But if you go there today, you will see they are putting so huge investments into science in all levels. The fellow that I've been working with, Professor Yao Tangdong, I met him when he was a graduate student. He now has 2 campuses, one in Beijing and one in Lhasa. And so they are really putting money into this. And the Chinese government is extremely interested in this issue, because if you take a river like the Indus River, 40% of the water in that river during the dry season is coming from melting of glaciers. Those glaciers are shrinking. That river flows through China, a nuclear power country. It flows through Pakistan, another nuclear power country. It flows through India, another nuclear power country. And they have not had good relationships through time. And so developing this communication across borders is a major effort, part of this TPE program. I just finished teaching a class at Ohio State. I teach it at the same time in Beijing, China, and 43 graduate students. Those students in China came not only from China, they came from Nepal, from Pakistan, from India, And their education is being paid for by the Chinese government for them to come there and get their master's and PhD. So they're putting a lot of resources into this. And frankly, you know, if this country does not support science, and there is a very strong correlation between the amount of money you put into science research and the GDP of countries around this world. And so this is our investment. Our young people are our investment in the future. And this is something we really have to work out. And we have to do it globally, because these problems will not be solved by people here in the U.S. They will not be solved by people in China or India. They will be solved by working together.
Thank you.
See?
Thank you.
Dr. Thompson, we have lots of questions. If you don't mind, we have two more. One from Bill Schaff over there in the corner, and then one from Gerald Meinwald. If you don't mind, taking two more questions.
We okay for
Sure,
time? Okay.
Yeah.
All right. Sure.
Bill Schaff there in the corner.
So
I'm told that there are two more questions, so you're not permitted to get off the stage yet.
Well, that's what they tell me.
Bill Shupp is my name. I think you once knew my father at Ohio State.
I did, absolutely.
And I'm at UCLA. You mentioned in passing, and I thought it was quite interesting, this direct correlation between the rise of methane in bubbles with warming. And it seemed to me that this group would be interested in methane in as much as it's a much more effective greenhouse gas than is carbon dioxide.
Methane is certainly important. It has, we talk more about carbon dioxide because methane has a residence time in the atmosphere of only 10, 12 years before it's oxidized into carbon dioxide. But the sources, when you looked at that history through the last glacial cycle, that methane is coming from the wetlands in the low latitudes. Now there's a lot of discussion of where, you know, methane in the last couple of years has really taken off again. And the question is, where is that coming from? How much of it is coming from the wetlands still in the tropics? How much of it is coming from the loss of permafrost and ice cover in the high latitudes where we have a lot of methane and carbon dioxide stored in a frozen state? So it is important. It is a very important part of understanding how the climate system works. Hope that answered your question. Yeah.
Okay.
Jerry Meinwald from Cornell University. You've given a beautiful account of all these wonderful physical measurements. I wonder, are there any organisms trapped in your ice cores, and are there biologists who are looking at the early microbiological world in those samples?
Excellent question, and I must say that my interest in microorganisms increased during the time I had my heart transplant, because I got one of these infections in the hospital that nothing will stop, and I was given less than 10% chance of surviving. But we know that 75% of the biodiversity on this planet is in these microorganisms, most of which we don't even know are out there. So we do have a program right now on that Glacier core that we just drilled. We have a postdoc that we're sharing between our group and the microbiology department. And we are looking at evolution, or attempting to look at, I should say, evolution of bacteria and viruses as they're preserved in the ice. Ice will preserve, it preserves DNA, and it's amazing in that field the advances have been made at what you can do. And so identifying what organisms are in there, how they have changed with time. To me, for all of these, it doesn't matter what your field is, it's the new questions that this archive can be used to answer that is the future of any field. And so I think that was an excellent question and very important question.
Thank you very much.
All right, thank you.